put your own photos into it, like stuff on your computer.
Oh yeah? As the spirit or sprite or whatever? That's pretty cool. I was thinking about making my own. I might do that.
You can make, simple games pretty easily using it. Yep. All right. Back to cisc310. Okay, I did adjust, some of the answers to exam one and regraded everything. I think about 3 people, got, something, got a slightly higher grade. Yes.
I have a question. I still got 41 wrong for plural. The answer was driver, but I put in drivers because it was like.
Oh, okay. I may not have fixed that one,
Yeah,
but I have fixed all the other ones.
You know.
Yeah, send me another, email because I fixed all the other ones. For some reason I skipped over one.
When did you make those adjustments, sir? When did you make those adjustments?
I made them last night, and then I had Moodle to regrade the entire class. So I think three people or so got some extra points because of that. So that's good. Nobody got any lower score, so don't worry. I'm not turning a correct answer into incorrect. I'm just allowing more accepted answers. So that's good. All right. So let's see here. We are doing our Scratch program, and it's 12 people have turned it in, and we have 2 more days to do it. Are there any questions? Has everybody started the homework assignment? Yep. Yeah. Okay. Are there any questions about the homework assignment? Any concepts that you want me to go over?
Yes, everything.
Sorry?
I seem to have the logic work.
Okay.
It's the whole program is just not working. I don't know.
Okay.
I can't get it to work.
Well, let's take a look at the homework.
I want to stop the whole class for this, for my problem.
Mm-hmm. Well, let's go ahead and take a look at the pieces that we need for this particular homework assignment, and we'll go ahead and use Scratch to do that. So we go to educational, Scratch. All right, so we'll have Scratch on one hand and then look at the homework assignment on the other hand. The first one is to pick a random number, and that's under operators. I think most people can find where the random number generator is. I'll just go ahead and point out where you can find that. And this window decides it doesn't want to give up its screen. All right, so go to operators. And you can find pick random 1 to 10. That's the default. If you just click on this block, it gives you a number. So if you click on it again, it gives you a different number. Supposedly this is random, but nothing is truly random in the world of computers. So this is what we call pseudo-random, because true randomness is actually very difficult. For those of you who are interested in computer security, you will find that it's really hard to get anything that is truly random, that is difficult to guess systematically. But for our purposes, this mechanism is fine. Okay? We have a mechanism to generate a random number. So getting back to the notes here. So what you need is a variable to store the solution, because you need something to store that random number. Because if you compare the user's guess to quote-unquote the random number generator, every time it can give you a different number, so it's not going to be the same number. You need a variable to store a single random number from the beginning of at the beginning of the program before it gets into a loop. Asking the user for a guess means we have to go to control, and because this process is repetitive, we have to ask the user again and again. So you have no choice but to consider the loops options. One loop option is forever, but that's not going to be that's not going to work too well, because we want to stop the program at some point. So we don't want to use forever in this case. Another option is repeat 10, or repeat a number of times. We don't know ahead of time how many times the user will take in order to get to the right answer. So repeating a certain number of times is not going to work either. we have forever if, okay? So that means that if the condition becomes false, it will get out of the loop. Maybe we can use this, okay? And the last one is repeat until. I think that's your best choice because it does allow you to specify some additional action after we get out of the loop. Like, saying, a message to say, congratulations, you got the right number, or you guessed it in how many turns, if you want to add to that logic. So this is the block that you need for your homework assignment. If the guess is greater than the solution, indicate so. Now, just reading this one English sentence, we already can identify a few components that you need for this program. The first one is the word if. In other words, we are trying to decide what to do because there are two options. One is if the guess is actually greater than the solution, we want to do something, which is using a say or a think block to indicate, hey, your number is too large or too small. Too large in this case. But if the guess is not greater than the solution, we don't want to do anything according to step 3. So that's a conditional statement. Okay? Any conditional statement has a condition or something that is either true or false that evaluates to true or false. In this case, this is the condition. If the guess is greater than the solution, it is a condition because it is either true that the guess is greater than the solution, or it is false, that it is greater than the solution. So in that case, we have to go to operators. And under operators, we have the comparison operators, and that's what you need in order to do the compare. Are we doing okay so far with this particular program? Okay. So getting back to here, the next item, number 4, is about the same, except it is only going to indicate whether the answer is the guess is less than the solution. And then here we have go back to step 2 if the guess does not equal to the solution. This tells you when to stay in the loop. So this logic has to be specified in the loop condition itself, because when this condition the guess does not equal to the solution, we want to stay in the loop. This is the stay in loop condition. If the guess matches the solution, indicate so and end the program. So you can do that after the loop exits. Just say, okay, you got the right solution, and then you can end the program after that. So are we kind of doing okay so far? Now it does have nesting already. In other words, we have some construct that will include other constructs. In this particular case, I can give you a hint. The conditional statements are inside the loop. So if you have it arranged, in the opposite way, it's not going to work. You have to have the condition inside the loop. Are there any questions about what I just said about the Scratch project? No questions? Yep.
Do we have to do it the same way you just explained it, or we can?
There may be other ways to do it. You can use messages to help you do this. So, I'll take a look. If it achieves the same thing as described here, I cannot mark you wrong.
Okay.
I submitted one. I kind of did slightly different, maybe a slightly more work, but it worked using broadcast in for
And receive.
and using if and else.
You can use that. That's a different mechanism. In fact, we're going to talk about how you can use broadcast and receive. And in today's class, we'll talk about, hopefully we'll get to what we call an activity diagram in the UML, the Unified Modeling Language. So we'll take a look at that. But if you can figure out how to use, broadcast and start when I receive, that's okay too. I think it's a little bit more complicated that way. Using what I just said, the constructs that I just mentioned is actually easier. All right. Any other questions? No other questions? All right. If there are no other questions, I will go ahead. Yep, go ahead. Row sheet.
Not really a question, but
A reminder. That's good. All right. So go ahead. Here's your row sheet. Okay. Oh, there's one more thing I want to mention. The other day, I was looking up information for one of my other classes, CISA 141, which is multimedia capturing and publishing. So I teach all kinds of odd end classes. But it was a fun class. It's a very fun class. And we were on the topic of digitizing tablets. Does anyone know what is a digitizing tablet? Nobody knows. A Wacom tablet. It's basically a piece of plastic, and it has a stylus. It's for artists, so you can actually use a quote unquote pen on a surface, and the difference between this and a mouse is the tip of the pen is pressure sensitive. In other words, it can sense how hard you're pressing on the pen, and it's a very precise type of equipment. So it's good for using AutoCAD, any type of CAD program, computer-aided design program, and also for artists who want to draw pictures on a computer. In other words, it's a digital canvas, if you will. And I was doing some research on whether it is still people still use that kind of thing or not, and people still do it. Okay, but it's not inexpensive. It's quite expensive. To get a tablet, a digitizing tablet that has a display behind it, is $700 for a smaller one, and for that money, you can actually get an iPad. Now, the difference between an iPad and a digitizing tablet is, with an iPad, even though it has quote-unquote pressure sensitivity because it can actually measure the contact area of your finger, it's not very precise. Okay. In other words, when you press on the screen, a touch screen, whether you're touching it very lightly or whether you're pressing really hard on it, it doesn't make that much of a difference in terms of the contact area between your finger and the touch screen. So it's not as useful as a digitizing tablet. And then what I found was a product that looks like this. Now I want to mention this here because eventually it will relate to this class. So just hold on one second. Let me go there. Digitizing. Look, this is a tablet. No, it's called a stylus. Stylus. It uses Bluetooth to communicate with the tablet. It's pressure sensitive. I cannot remember the brand name, so I have to look for it. That's it. Jot. Okay, so that's it. This is the tool, and it's really quite neat if you look at it. And I'll show you a picture of it. So it looks just like a pen. We call it a stylus, but it's basically just like a pen. It has a tip. The tip has a little plastic, a flat piece of plastic at the end, so it will kind of stay flat on the surface of any tablet, like an iPad or an Android tablet. But it's pressure sensitive at the same time. So when you press harder on the pen, it transmits this pressure level through Bluetooth to the iPad or the Android tablet that you're using it with. So people can use it for a lot of different things. And if we look at the applications supported by this particular device, you can see what other people have done with it. You can use it as a brush because you can brush harder, press harder, or not as hard. Sketch and keep going. You can also use it as a. You can see the hair is actually man-made. I mean, artificial. It's created by using the software. But the downside, there's only one downside from my perspective. All these apps are iPad apps. I was trying to see if I can get it for an Android tablet, and there's none yet. Okay, so once again, it means the hardware devices are ahead of software. It's not like the manufacturer. This is the manufacturer, Adonit, I guess. It's not like the manufacturer has any affiliation with Apple and decided, oh, okay, we don't want to make any software for Android. It's only because people who use Apples or the applications designed for Apples are more inclined for artists, and that's why they support the device like right off the bat. As soon as they found out, hey, there's a pressure sensitive stylus for this device, people just jumped on it and go, okay, we'll make use of the hardware because we have been waiting for a hardware like this for a long time. Whereas people using Android, tend to be more kind of business or hacker type. So less attention is paid to artist type of programs. So I think that's an interesting point because hardware is ahead of software. I cannot use that device because no one has written the software to make use of the Bluetooth device. So that really kind of shows you the possibility in software development, because with tablets and smartphones and whatnot, there are so many possibilities. And we are just really scratching the surface in terms of exploring those possibilities. All right, so let's get back to our class, and we are now in topic 5 / topic 6. Topic 5 talks about programming functions, overview of languages. We just talked about that last time. I briefly talked about flowcharting or pseudocode techniques. I can talk about flowcharting, but I really do not recommend flowcharting because flowcharting really doesn't help much, in my perspective, because it encourages spaghetti coding. It's okay for simple logic, but when you have anything that's more complicated, it's really it can mess things up really quick. Pseudocode is basically coding, but without using any programming language, so you don't have to deal with syntax errors and stuff like that. We have typical computer instructions and structured programming concepts and techniques. Typical computer instruction. Now this one, if I just look at this phrase here, it doesn't say what it means when I say typical computer instructions. When you read the textbook in earlier chapters, some of you probably still remember, and I mentioned this last time, computer instructions or instructions intended for the processor is just a long string of zeros and ones. Do you guys still remember that? And that's the most native computer instructions. The processor only understands that sort of instruction. And that's why we have programming languages. Do you guys remember from last time that we talked about programming languages? Let me just start it up again so I can show you what I mean by that. And it's under Free Mind in last Thursday's class. There we go. Do you guys still remember this picture? Okay, we talked about computer programming languages, and it's separated into basically 3 main categories. One is called compiled, one is called interpreted, and one is called hybrid because it runs on virtual machines. And then we have a 4th one called machine language, and that's basically what a computer processor natively understands. Are there any questions about this picture? Where do you think Scratch falls into?
Hybrid.
It's a hybrid. Yep, it is a hybrid. Because it is a cross-platform type of architecture, and there's a little bit of difference because there's no compile. Okay, there's no compilation because as you construct the program, you are already indicating the structure of the program. There's no separate step to compile the program into the underlying structure of the program. When you look at a typical program, okay, I can show you a typical program. And we'll just go to, Pascal, bubble swap. Okay, so this is a very typical program. Yep, there you go. So this is a very typical text program. The programming language is kind of old and nobody uses that anymore, but it still represents a fairly easy to read type of text program. This type of program requires compiling because the computer really only sees the characters. In other words, let me skip the comments section. So as far as the computer is concerned, it's really literally just seeing program space sort, open parenthesis, input, comma, space, output, close parenthesis, semicolon, space, line feed, space, const for constant, and so on and so forth. In other words, there's no inherent structure. We can see structure because of the indentation. Okay, by means of indentation, I mean the spacing from the left margin to the first part of the program. So we see structure only because we can visually see the indentation, and that helps indicate the structure of the program. But a compiler or the computer doesn't see it. The computer only sees this whole thing as one long string of characters. That's all that the computer sees. There's no structure. And the compiling process converts this entirely linear structure into the structure of a program. But when we look at Scratch, okay, when we look at a program that we have written in Scratch, we'll just bring up the program from last time. We have to go to my account. And last time we met, it was on the 1st. When we look at a program using Scratch, let me just make this area a little bit bigger. It's already structured. As you input or type the program, it is already structured because the way we drag a block in and we drag other blocks into an earlier block, that's already giving the program structure. So there's no separate compiling process using Scratch. It saves the environment, the trouble of compiling. Now that is really nice because if you have to compile, let's go back to the Pascal program here. What if this end is missing? What if for some reason I just missed that end? It will then interpret this end to end that begin. And there won't be another end to end this begin. So the nesting of the entire program will be messed up. And it will give you an error message, and the error message will have nothing to do with missing an end here. It will say that it's missing an end somewhere, but probably not at the right place. Okay? And that's a typical problem with a programming language is when you do make simple mistakes, a typo or something that's really simple, the compiler or the interpreter will give you an error message and say, I don't really quite understand this program. It's not following the rules. But the complaint or the error message a lot of times has nothing to do with what we see is the problem, because we are seeing the problem as, oh, we're missing an end to end the while. But the compiler doesn't know that the missing end is with the while. It's just saying that I'm counting the begins and the ends. It's not matching. That's all it's going to complain about. Okay? But when you use an environment like this, it cannot happen. There's no way you can begin a conditional statement or a loop without a matching end. And that's why I think this is a really great way to start programming, because you don't have to deal with that sort of a problem. Are there any questions at this point? There's actually another programming environment very similar to Scratch. Can anyone guess which one it is? It's intended mostly for kids, but I think it's not a bad programming environment. Does anyone have Legos? Particularly the robot kids? Lego Mindstorms? No? Has anyone heard of Lego Mindstorms?
Yeah.
Yep, okay. So let me just bring you guys to Lego Mindstorms. Mindstorms. Particularly, we want to look at programming. We need a screenshot, so we go to images. And you can see that, just like with actual Legos, a Lego Mindstorm program is also just made out of blocks. But it's not quite the same blocks that we are used to in Scratch. This is actually not procedural. It is actually, it's different. Okay, it uses a different type of programming. But nonetheless, it is also graphical. Lego Mindstorms. Do you guys know what Lego Mindstorms can do? No.
Is that like a schematic right there?
Yeah, it's more like a schematic than an actual programming language. It doesn't specify the steps to perform. It specifies how the blocks relate to each other. The input of this block, is coming from the other block, and then the output of this block goes to the other block. And then at some point, they will have to merge and control the motors and use the sensors as input. Go ahead.
Basically like Legos, but with robotics. They have like motors, sensors.
Yep.
Lots of different.
Yep. But there are amazing things you can do with Lego Mindstorms. I know I'm getting a little bit distracted here, but I think it's really nice because you can see what people can do with Legos, right? I mean, you think of Legos and you go like, yeah, I used to have that, but you can still play with Legos. I'll go look for Mindstorms. I think it's a Segway. How do you spell Segway?
I just type it in and see what Google has to say.
There you go.
And there is a video. This is really impressive. You know, I don't need to turn on the sound, but it's actually quite impressive. There we go. So the main screen is actually what we call the brick of a Mindstorms kit. You know, that's basically the brain and also the housing of the battery. And that's it. The robot is running on 2 wheels, just like a Segway.
Not falling too.
And it's not falling, it's balancing. It's sensing, you know, which way it's tilting just a little bit, and it will compensate, you know, the tilting by moving its motor or moving its wheels, turning its wheels to balance itself. This one is not as impressive as some of the other ones I have seen. You know, there was one where, you know, it can actually, someone pushes it to try to, you know, make it tip over, and if it self-corrects. It's like, you cannot push me down. I'm not going down. So that's one. And if you want something that's impressive, there's another one that can do a Rubik's Cube. It has the sensor and also the mechanism necessary to do the Rubik's Cube. How do you spell that?
Rubik's Cube. R-U-B-I-X. Oh,
And then we'll say
Right, so it's
Mindstorms.
second.
R-I-K.
Yeah. Rubik's. How many
There we go.
algorithms did that guy learn? Just one. Spinning.
It has sensors to sense the colors too. So, you know, it's actually trying to solve the problem, and also, you know, doing the robotic thing to actually mechanically turn the cube. I think it is really cute. I think it's really cool. So when next time we think about, you know, playing with Legos, you know, we can think about playing with Legos in this particular way.
So you can get it.
It will solve it. You know, I think the video actually is going to fast forward it, or maybe this is not a tough problem. It's tough for me.
It's almost good.
Yeah.
Yep. One more turn.
And it failed.
Yep. It'll get it. There we go. Yep.
Had to have a computer to report that.
There you go.
Yep.
Machine, I'll do it for you.
Right.
Ooh, look at this one. 20 by 20 by 20.
Oh, one of those.
And then we will build an ND1. You know, I think that's from Star Wars. The Walker.
Oh, the AT-ATs or the chicken walkers?
I think it's a chicken.
ATSTs.
Some interesting Rubik's cubes. There's one that's silver where the blocks get smaller as you go in.
So there you have it.
So
But this one is not as interesting from the programming perspective. It's a nice mechanical design, you know, so you just have to turn the motor and it will walk. But there's really not a whole lot of software involved in this particular one. So
What motor is that for?
I think there's only one motor.
Is that like just a Lego motor you can buy for?
No, this is a Mindstorms motor, so it has to connect to a Mindstorms brick to control it. Yep. So this one is okay, but it's not, you know, as impressive as the Segway, you know, and also the Rubik's Cube solver. And this one is just walking. I mean, there's no control whatsoever.
It was basically just building it.
Yep. And also figuring out mechanically how to make it work, you know, that's the interesting part, you know, how all the linkages work. So that's the interesting part of this project, but it's not really different or difficult from the perspective of software. All right, I can see some people stopping by Fry's, you know, after the class, you know, to pick up a Lego Mindstorms kit. But it's fun. It's really a lot of fun. Scratch is also, you know, the programming interface of a particular kit for kids who has motors and sensors and stuff like that. But I cannot remember the name of the kit. But you can use scratch blocks to program something that's external that moves around. So it's a lot of fun too. All right. So do we have any questions about this particular program and how you might be able to borrow some of the blocks here for your homework assignment? Question?
Oh, when you do the homework assignment, when you go over here, where you've got your actual sprite and everything, make sure you right-click on your variable and click hide. Otherwise,
click.
Or you could go to
right-click
variables and uncheck it.
Yeah, make sure you click hide or uncheck it like he said. Otherwise, you'll be able to see the answer.
That's cheating. Nobody likes it.
Oh. Well, it's only when I grade it that I have to do it that way if I want to have fun with
I
it.
put mine away. Mine's already ready. You just have to click the green flag and
Yep.
start it. Hit full screen.
All right. Cool. All right. So now we're going to move on to a slightly different topic because this is topic 5. It really just talks about programming and stuff like that. Topic 6 talks about developing flowcharts and writing computer programs, analyze problems, develop solutions, design flowcharts, and write and execute programs. So these two topics actually have, I think they have the order reversed. And then topic 7 is also related to topics 5 and 6. It's called systems analysis and design. So we'll go ahead and start to talk about the other aspects of programming. Are there any additional questions of topic 5, particularly related to your homework assignment, and also the different blocks that we use in that particular program? Okay? So you have all the building blocks already. So now the question is, how do you use those building blocks to make a program that's actually useful, that can be used to solve a problem? Okay? Let me give you a problem to solve. Okay? I give you a stack of cards. Okay? Just maybe a bunch of numbers, and you have to help me sort it. Got to make sure that I use one that is not permanent. Otherwise, it will be bad. Okay, so we'll look at 2, 5, 1, and 10. That's 4 numbers, and I want you to sort these numbers in a non-decreasing, or in this case, it's increasing order. It's not hard, is it? Okay, you take a quick scan of these numbers and you say, okay, 1, 2, 5, 10, done. But exactly how did you do it?
You compare each number.
You compare each number. Okay.
5,
Take the
bigger, smallest one.
Okay.
Compare it like 2 to 1.
Okay, that's one way to do it. You're using what we call selection sort. Okay, that's called a selection sort mechanism. In other words, if I give you 100 numbers, so it's not easy to just eyeball and find out what is the right order. If I give you 100 numbers, the easiest way to sort, is to scan through the 100 numbers. Pick the smallest one, move the smallest number all the way to the left-hand side. You have 99 numbers left. Do the same thing with the rest of the 99 numbers. Okay, go through them, find the smallest one, put it next to the smallest item. Then you have 98 items. Do the same thing, and you can do this until you have 2 items. Then you just swap, whatever, swap if it is necessary with the last 2 items, and you're done. The next question is, now that you know how you do it, systematically, can you write a program to do it, using that method? That's what we are talking about in topic 6. Topic 6 is basically saying, okay, let's assume that you know how to solve the problem. Can you, write down the systematic way of how to solve a problem? What do you think? Think we can do it?
Yeah. Awesome.
It's possible. Okay, so the flowchart idea is to use a flowchart, what we call a flowchart, to represent the logic. Now flowcharts are not really quite like Scratch. I will show you what a flowchart looks like. So let's go to graphics. And I may not have, let's see if LibreOffice has the blocks. And it does. Okay, if you go to LibreOffice and you go to basic shapes, it has all the basic shapes that we need for flowcharting. I'm just going through this because it has a different library for just flowcharting too. for flow charting, all we really need is just a block, like a rectangle, and a diamond, which represents a decision-making point. Okay, it's better to use it, I think I'll just use the whiteboard, for now. All right. As far as we are concerned, in this class, flow charting has 3 symbols. Okay, I take it back, not only 2. You have the rounded edge, symbol. So this is either for starting or stopping. Okay, so start, stop. So they can only be originating the flow of logic, or they can only be the sink of logic, which means no other steps can come out of this. You have a diamond to represent a decision. So it has 1 way coming in and 2 ways of going out, or it can also be used as a merge mechanism. You can have 2 way of coming in and only 1 way to get out. And then we have the third block, which is a process. A process is just a rectangle, 1 way to go in, do something here, 1 way to get out when that something is done. And that's all there is to it, to basic flow charting. Okay. If I use this type of flow charting and we go back to the Scratch program, and we'll just go ahead and concentrate on one part of the program. We'll just concentrate on this one here. Okay. So this is the block of code that I want to use flow charting to represent. How am I going to draw a flow chart according to these particular blocks?
The decision would be like an if-else statement.
Well, a loop is also an if-else statement too. So it's, there's no, how should I put it? There's no structure. When you look at a Scratch program, it has structure. In other words, the if, this one has an if, else, and it has to end. Inside we have an if, else, and it has an end. And you cannot miss any component. I mean, each if must have an end. When you draw a flow chart according to this logic, you can make a mistake, and you can change the logic, you can change the meaning of the logic very easily, because there's no enforcement of this is the beginning of an if, it must have an end according to the rules. There's no such rule. So that's why I don't really like using flowcharts, because it's really not. I think it's not a very clean way to represent logic. So if we don't use flowcharts to represent logic, what are we going to do? Well, the next question is, why do we even bother? Why don't we just, when we have a program to write, why don't we just start writing the program in the programming language? Well, some of you are going to take cisc310 eventually. So you can say, okay, I'll just sit down and start writing in C++. Okay. Is there a problem with that approach? How do you solve a problem when you have to write a program to solve a problem? What would be the steps?
I don't know.
Before you start writing, you have all the ideas, all the steps you can write. What
Yep.
you're gonna condition it.
Right? So, well, the first step, you have to do it by hand first.
Yeah.
Okay, before you can write a program to solve a problem, you have to be able to solve the problem by hand first. Just like with sorting, okay? But I cannot use sorting as an example in this class, because sorting involves the concept of an array, and we have not talked about arrays in this class, and neither will we talk about arrays in this class. So I cannot use that as an example. We can look into some other problems that we can solve. I have a quick and easy one. Determine whether a number is prime or not. That's a pretty easy problem to solve, right? So let's use that as an example. So we'll go through the thought process, and as we go through the thought process, we'll think about how do we represent the concept and the ideas that is going through our mind. Okay? So once again, we have to do it by hand first. If we don't know how to do it by hand, we won't be able to write it in as a program. Okay. So I'm gonna check this out because I don't want to talk about flowcharts. Instead, we'll talk about how to find out whether a number is prime or not. All right. That's a whole lot easier. We can go just look, use a notepad, and I can give you an example. 5. Is that a prime number? Okay, did you guys just go through some systematic logic to determine whether 5 is prime or not? No. You just look at the 5 and go like, yes, 5 is a prime number. Done. Okay, I don't have to go through any logic. Okay. Next number. Let's go through. Let's look at this number here. Okay. 762. Is that a prime number?
No.
No. Well, how come you don't? You know it's not a prime number. It ends with a 2. Okay. Is that systematic? Kind of. Okay. Let's look at the next number then. Okay. Let's look at 891. Oops. 891. Is that a prime number? It is not a prime number because when you add up the digits, it is divisible by 3, so the number itself is also divisible by 3. Is that a systematic approach? Kind of, okay? Because it is a rule of thumb. It's also called a heuristic. But a heuristic is really just a heuristic is a rule of thumb. It's somewhat systematic because we can use it to check, but it's not easy to program in the program. Okay, let's try another number so it's not as obvious. What about this number? Is that a prime number?
Yes.
How do you know? It looks like a prime number. So this time we run out of all the tricks that we already know, don't we? The last digit does not end with a 2, 4, 6, 8, or 0, so we know it is not divisible by 2. It doesn't end with, if you add up the digits, the sum is not divisible by 3. So we know this number is not divisible by 3. What other tricks do you use to determine whether a number is divisible by a certain number? 5 and 10s are easy. Okay, divisible by 5 means the last digit has to be a 5 or a 0, and this one is not. So when we run out of all the tricks that we have, then we have to use a very systematic approach to do it. I know it's a very long and boring process, but what do you have to do now? You have to try to factor it. Okay, how do you factor a number?
Start with itself and 1 and
Okay. So let me give you this approach here, and you tell me whether I'm wrong or not. Okay, I will use this number divided by 2. It'll give me some number at the remainder of 1. Then I can say, okay, it's not divisible by 2. Did I do something that's wrong? Is that the right conclusion? A remainder of non-zero means it's not divisible by 2. I'm correct, right? Now, it's not really the smartest thing to do because we look at this number and go like, we don't even have to try this. We know it's not a even number, and so it's not divisible by 2. But it's not wrong to check it again. So the next item is to say, well, if it's not divisible by 2, let's try 3. And it's going to have a remainder of, okay, how about just non-zero? Okay, it has a remainder of non-zero, so I can now conclude it is not divisible by 3. Is that a wrong thing to do? Is it a wrong conclusion? It may not be the smartest thing to do, but it's not wrong. Okay. Next, I'll use divisible by 4. But heck, that's really dumb. Yeah, that may be really dumb. But the conclusion that it is not divisible by 4, is that a wrong conclusion? It's a good conclusion, right? It is definitely not divisible by 4. Now, there is a reason why I use 4 and 5. The next one is 5. And this one I know has a remainder of 1. And it's not divisible by 5. And you know what? The next one, I will try 6. Even though I have tried 2 and 3 already, I'll try 6. And some non-zero remainder. And the conclusion is the number is not divisible by 6. And so on. Yep.
You just make the program or have the program divide by, like, I guess, the number that did the numbers 1 through 10, and then if there's a non-zero remainder, then it's not prime.
Well, the
Are
question
they
is
prime?
how far do I have to go to make a conclusion that this number, when do I stop?
The number divided
Half?
by 2.
Oh, I can actually do better. I only have to go up to
5
the
minus
square
1.
root of the number. So this number is 1, 0, 0, 0, 0, 0. So I guess the root is what, 300 something? I don't know. What is the square root of that? I only have to go to the square root. Okay, so now I have a very general approach. I can use a spreadsheet to do the rest. Okay, a spreadsheet can be used for many, many different purposes. One of them is here. Okay, so we'll go, is that the number? 1 too many zeros, huh? I think that's the number. All right, so what we'll do is we'll try out potential factors. So potential factors, we start with 2, and then we'll have another column to indicate the remainders. Okay, remainder. So the remainder is the mod operation. You don't have to understand a whole lot of this. I'll explain it later. The mechanism is not important. The concept is. So I will just use a dollar here, a dollar there. Okay, there we go. Next one is 3. It's a remainder of 2. And if I just do this part here, hey, that's pretty handy, right? And we know that this number is actually divisible by 11. And we're done because we have one, remainder being 0, so we know the number is not prime. Okay. Is this approach systematic? I think it's pretty systematic. The next question is, do you think this is relatively easy to code in a program like Scratch or whatever? Now, if I were to use only prime numbers, with the potential factors, that would have been a lot more difficult because, how do I get the prime numbers? Well, I either have a table, of all the prime numbers, or I have to figure out prime numbers on the fly. But this way, hey, I don't have to worry about, prime numbers whatsoever. I just try out numbers that are already known to be composite. But you know what? It's not going to give me the wrong answer. It won't identify a number as a prime number when it is not prime. So it doesn't matter. It does make the program a whole lot easier to write. Do you think we can code this in Scratch? Now that we know, yeah, that's pretty systematic. Yes? Kind of? Let's try it. Let's give it a try. Okay? Let's give it a try and then see how we can code this, in Scratch. Okay, so we'll switch back to Scratch right here and give ourselves a new program. And I'm going to make a new folder to save, today's note because I think somebody might want to go over this again at some point. So today is 2012 11/06. And this is cisc310. All right, so back to Scratch. There are different ways of writing a program, but Scratch makes it makes different approaches easier to test. So what we want to do is to go back to my spreadsheet here, and then we try to analyze what we have done with the spreadsheet, and then try to come up with the equivalent construct in Scratch, and we'll build a program step by step. Okay, Scratch is really good with that sort of thing. First thing is, how do I get the remainder of a division? It seems like that's really important in this program. Yep, right? Okay, so let's go back to Scratch here, and then we go through the operators and see, which one may be useful for this purpose. What do you think? How about this one here, the mod? Mod is actually the short form of modulus. which is basically, it means the remainder of a division, okay? So I don't really know about that one, so let's go ahead and give it a try. What do you think is the remainder of 11 divided by 3? What is the remainder of that?
2.
Okay, we'll try it. Click. It says 2. Okay, so it seems like our understanding is correct. But let's give it another try here. How about 16? What is the remainder of 16 divided by 3?
1.
Should be 1. Try it. Oops.
It's not there.
Click it. 1. Okay, so it seems like we have identified the right operator, between divisions. Okay, that's good. What else did we have to do in this program? Okay, we need somewhere to store the number that we are trying to determine whether it is prime or not. Okay,
Well,
how do we do that in Scratch? How do we remember? Hey, this is the number that we are trying to determine whether it's prime or not.
I think the mouse literally is hovering over.
Yep, exactly. It is a variable. Okay, so we need a variable to store that number. And I don't really have a particular name for this variable, so we'll just call it n. Mathematicians like really short names. All right, so we have n here. And to make this program work properly, maybe we'll make it fancy already. So we'll go to control, we go, when the green flag is played, we go to sensing, and then we just ask the user for a number. Okay, enter a number greater than 1. Oh, by the way, is 1 a prime number?
Yeah.
No,
It's not.
it's not. 1 is not a prime number by definition.
This is no other
What?
number
By
is-
definition? How would why would someone be so insane and define 1 as a non-prime number? Well, that's not a question I can answer, but I can only tell you that a non-prime
Because
not
it cannot be, it can't be divided by anything but itself.
Yeah.
A prime number is divided by itself and 1, or divisible by itself and 1.
But since I trust Wikipedia, my answer is a lot easier than that. I just have to say a prime number is a natural number greater than 1. Ah, so that means 1 itself is not a prime number. All right. So there we have it. All right. So I asked the user to input a number greater than 1, and for the simplicity of this program, I'm not going to do error checkings. Okay, I'm not going to check whether the number is actually greater than 1 or not. You should do it if this is a program intended for end users, but for ourselves, for this class, I just want to illustrate the logic, the main part of the logic to determine whether a number is prime or not. So I'm going to trust the user will input a correct number. And then what we need to do is to use a variable and remember what the user has just input. So I use set n to answer to remember the actual number, and from here on we can just use n instead of answer for the rest of this program. All right, so that's good. And you know what? I'm not going to do a whole lot more than that. Just run the program. It asks me for a number. I'll just go ahead and type in a number. Let's say 20. Okay. And what I want to do here is to change this 16 mod 3 to n mod 3, because it looks like we should not be using a constant. We should be referring to n, in the mod operation. And it tells me n mod 3 is 2, which is correct because n is 20 at this point. All right. But if you look at this operation, modding 3 or modding 2, is that what we want to do, is to use a constant as the divisor? Let's go back to the spreadsheet here. In the spreadsheet, I have a different potential factor, which is our divisor. So how can we change the potential divisor? Go ahead.
Make a list.
I don't need a list. I really don't need a list. It's actually a lot simpler.
We need a variable.
A variable, very good.
And 1.
So we'll go ahead and create another variable. Now, what is telling you that these numbers will need a variable to store? They're changing over time. Okay? Because the first time I tested it was 2, the second time is 3, and then 4, 5, and so on. So it's changing. Anything that's changing over time is a variable. It is changing. Okay? Variable. Okay? All right. So let's go back to our program. I cannot use n. N has a purpose already. I cannot use n for this purpose. So I have no choice but to make a new variable for this purpose. Okay, I'm just going to use f as the name, f for factor. Okay, and so the mod operation will be n mod f. But f has to change. Okay, what is the start value of f? Let's go back to the program. It's 2. Nope, it's 2. Because that's the first potential factor that we tried. Okay.
I thought you were talking about when it starts, when Scratch starts.
Oh, I meant when we ran the algorithm, when we tested the potential factors, we started with 2. Okay, sorry I wasn't clear.
So we set f to 2.
Yep. So we want to set f to 2, but just once, right? All right. So that's good. So we'll go ahead and run the program again, which doesn't do a whole lot. Okay, we'll try 20 again, and then we'll click this. It tells me 0. So it's telling me that 20 divided by 2 has a remainder of 0. That's right. That's good. Okay. All right. What else do we need to do here? Well, it looks like we have a decision to make. When we divide 2, okay, let's change this number to 20 to match. Okay, 20 is not very exciting. Let's try 23. Okay, there we go. So when we change n to be 23, we first try. Okay, 23 divided by 2 has a remainder of 1. Can I stop? Can I stop right here and say, well, 23 is prime because it's not divisible by 2?
No.
Maybe it's divisible by some other numbers, right? So then we have to increase the potential factor f by 1 and then try it again. Okay, 23 divided by 3 has a remainder of 2. Can I stop now? No, I have to keep going. So do you think I need a conditional statement for this, or do you think I need a loop for this? Because it looks like I have a decision to make. Okay, whenever you have a decision to make, you can think about using a loop or a conditional statement. The difference is a loop allows you to do something over and over again. A conditional statement simply says you have 2 ways to proceed, but the 2 branches have to merge at the end, and it doesn't go back to the beginning. Which one do you think I need? A loop. Okay. All right, that's a very good starting point. So we go back here, and then we go to control, and then we go through all the loop concepts. Okay, so I'm going to display all the loop concepts up here, and you can tell me which one is probably the best one to use.
Repeat until whatever.
Repeat until. All right, that's the right one. Forever means we won't stop. We don't know exactly how many times we have to go through the loop. This is another forever. I probably have something else to do after the loop. So this is the right one. Okay, so we'll stick it here. All right. Now we know whether when we get out of the loop has something to do with the remainder of the division. But I can't just stick n mod f into here because n mod f gives me a number. It's not something that's either true or false. How should we modify it?
N mod f equals 0.
Exactly. Okay, so we need a comparison to 0. All right, so we go to operators, a comparison, stick this into one end of the comparison, and then just specify a 0 on the other end. Yep.
Wouldn't we put that into OR? So blank or blank, and then the other one be the square root, or you reach the square root of the number?
Well, this will work. I'll optimize the program later. Okay. So this is another tip for programming. Especially for those of you who will take more programming classes. Don't think about optimization or how to make the program go faster until you get it to work first. Okay. So what I'm doing here is to make the program as simple as possible, even though it's not efficient. It is simple, and so I can debug it easily. Once I get it to work with a simple version, even though it's kind of longer and more tedious, I can then think about optimizing it. Okay. All right. So this is good. If I run this program now, what do you think it will do? Let's give it a try. Okay. So I'll give the program a proper end to say stop script here. and we'll just go ahead and run the program. Can anyone guess what the program will do when I type in a number, say 23? It's asking me for a number. Let me make the interaction screen bigger.
Well, just keep going.
It would just keep going. Exactly. Why does it keep on going? Like, zzz, nothing seems to happen.
Nothing, it would be
Any logic in there.
Exactly, because n has a number, right? N is 23. F is initialized to 2. 23 divided by 2 has a remainder of 1, which does not equal to 0, which means I'm not getting out of the loop. But what am I doing in the loop to change this condition? Absolutely nothing. So that means by the time I go back to the beginning and check the condition again, it would not have changed because I didn't do anything in the loop to affect either n or f. So n mod f will still end up as a 1, which is not 0, and it will keep going like that. So what do I need in the loop? I need to do something in the loop to change either n or f. But I cannot change n. I cannot change the problem itself. I'm trying to solve the problem, not to change the problem to something that I can solve. If I just want something that I can solve, I can just initialize n to 2 and I'm done, right? 2 is divisible by 2. I can get out of the loop. I cannot change n. I can change f. How should I change f?
Add 1 to that.
Just add 1 to it, right? Bump it up by 1. So I have a really nice construct to do it, which is change f by 1, and that will increase f by 1 for in each iteration. So this time let's go ahead and run the program again. And once again I use 23, and the program exits when f equals to 23. It makes sense, right? 23 divided by 23 has a remainder of 0. Very good. So if I go back to the program, I can actually make this program work at this point. When the loop gets out, when I get out of the loop, what type of checking should I do to determine whether the number is prime or not? You have to kind of go back to the definition of a prime number. It is a number that's divisible by 1 and itself. It's only divisible by 1 and itself. Okay, so I'll let you guys help me fill in some of the details here. I will do the simple part and you guys have to do the hard part. So I'm going to do the say and the say here. And I'll make these really simple. This one will just say the number is prime, and then the other one will say this number is not prime. The question is, what do I put into the condition here? Well, we only have so many options, right? Because we only have 2 variables, n and f. So the question is, what is the relationship between n and f that will confirm that the number is prime?
If f equals 1, say it's prime.
If you're getting close.
If f equals f.
If n equals f. Okay, when n equals f, after we get out of the loop, the number is prime. Because if the number is a composite number, it would have exited earlier. F would have been a smaller number than n itself by the time we get out. Is that making any sense? Okay, so let's go ahead and give that a try. Go to control, operators, because it's a comparison. So it's an equal comparison between n and f, like so. Run the program again. Let's try 23 again. The number is prime, but I really need to test the program again with a composite number. Let's pick a tricky one, like 25. The number is not prime. Very good. Let's try another tricky number. How about 91? 91 is not a prime number because it's 7 times 13. The number is not prime. Very good. Let's try 101, which is a prime number. It's taking a little bit longer than it should. All right, so this is really good. This is cool. All right. I have just written a program. Even though it's not efficient, it does solve the problem. It tells me whether a number is prime or not. Okay, but it's not efficient at all. Okay, so for the rest, let's just do this for the rest of today's class. Okay, and some of you will get absolutely bored by this section of the class because I will tell you how we can optimize the program and prove to you that we can do it that way. Okay, so getting back to this program here, I mean the spreadsheet, I'll go to, I'll change this number to 101. My claim is by the time I know 101 divided by 11 has a remainder of 2, I can get out at this point and conclude that 101 is a prime number. There are no factors. Okay?
Taking the square root of the closest whole square root.
Right. Yeah, but can I prove to you that that is always the case? That's the question. Now, some of you will think, okay, let's try it out with 97. Okay. All right, let's try it out with 97, which is a prime number, because the square root of 97 is a little bit less than 10. By the time we test 10, it doesn't have a factor anymore, and according to my logic, it is a prime number because if I cannot find a factor by the time I get to 10, there are no factors other than the number itself. That's my claim. Well, the only way you can test it is to try out different numbers, right? You can try out 81. 81 is definitely not a prime number because it's divisible by 3, and so we can detect that way before we try 9, it's already concluded that it is not a prime number. But how can you prove, or how can you know for sure that what I said is correct for all prime numbers? That you only have to test up to the square root of the number to confirm it is prime. Or if I flip the argument, how can you be sure that there's no composite number where it has a factor that is greater than, that it doesn't have any factor less than the square root, but is greater than the square root? That's the question. Yep.
For one of the numbers to increase, if you're like multiplying something with something else, the other one would have to decrease. So anything higher than the square root would also have a number that is multiplying with that's lower already.
Exactly. So that's the right, logic to the argument. But is that a proof? Well, it's not a proof, right? I mean, it's the right argument. Okay, you got the right point. But to prove that it is correct, is a different story. Okay. So why do we want to prove something is correct before we make use of it in our programs? So make sure it works correctly. What if I have something that seems to work most of the time? Can I just kind of make an assumption and say, this is going to work, we'll just put it into the program? No, why not?
Because that instance where it doesn't work is possible to show up.
It's possible to show up, but I'm thinking that I'm only staying with the company for 3 years, so it'll be somebody else's problem.
It'll look bad.
Nobody can trace it back to me, right? Well, so for that segment, for this particular explanation, I have to kind of go back in the past and tell you what happened in my graduate school years. It's really kind of funny. I hope you guys won't encounter the same experience. So with my dissertation, I had to use a particular theorem. A theorem is basically something that is known to be true in mathematics. Okay, that's a theorem. Something that is proven to be true. I should make it more concrete. It's something that is proven to be true, is a theorem. Something that is given to be true is an axiom. Okay, and there are lots of other things in between, but it's a theorem in this case. So my dissertation was supposed to start with a theorem and say, okay, we know this is true. It is proven that this is true, so I can use it as my as a basis. For about 6 months or so, I look at that, go like, yeah, that seems to make sense. So I was using it as the basis of my dissertation. But at some point, I decided, it looks kind of fishy. I really want to see, whether it is true or not. Okay, I want to see the proof that proves that it is true. So I went to my advisor, and said, well, Armand, I really am not sure that this is actually true all the time. So can I actually read the proof of this, theorem? And he said, well, this is actually a theorem proven by somebody else's, master's, thesis. So, so I went to dig up the master's thesis, and try to locate the proof of this theorem. There was no proof, okay? There was no proof. There was one sentence saying, obviously, blah, 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 has to be true. That was it. Okay? You know, in mathematics and in any type of hard science, every time you see obviously, blah, 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 those are usually considered famous last words. So anyway, I looked at the obviously, blah, 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 and goes, it's not obvious to me. You know, it mentions some other things before that sentence, but it's not obvious that they are mathematically connected. Logically, they're not. They don't seem to be connected. So I went to my advisor again and asked him, you know, well, it just says obviously. Is there any more concrete proof? And he said, no, you know, we have already, you know, the master's thesis was already approved. The guy already got his master's degree and had, you know, moved on already. So I just didn't feel comfortable. My advisor said, don't waste time, you know, with this, you know, it's already done. And I said, you know, well, I don't know about that. So I spent an entire week to come up with a counterexample. To prove something is right is hard, but to prove something is wrong, you just need one counterexample to show it is not right. And I did. So in a week's time, I created a scenario as a counterexample and went back to my advisor and said, well, you know, I can prove the theorem is wrong because I can find a counterexample. My advisor just said, oh, I guess it's not true then. It was really casual. I went back to the computer lab, you know, with my with other students who were, you know, working on a similar project, and I told the other student. He was a master's student and he was almost done with his own master's thesis based on, guess what? The same theorem. And he just went ballistic.
Yeah.
He said, I'm just gonna cure mine, you know, and so he was really angry. Huh?
Find the guy who wrote that paper and get him.
But that really shows you why it is important. Okay, what if, you know, the software or the, you know, the stuff that the research we were working on, what do you think will happen if that research, you know, is to be, you know, put into a space probe, you know, sent to outer space? We'll be the laughing stock of all the alien species. They look at our program and go like that, you know. Yeah, it's not worth it to invade, you know, Earth. You know, there's nothing worth, you know, invading over there, right? Inferior species, you know, it's like, yeah. There's no way they can, you know, they can be a competition in conquering the galaxy. Just leave them alone. They will blow themselves up first, you know. All right, so that's important. Okay, you know, proving something is correct is actually important. So in this case, how can I prove it? Okay, he got the right concept. Okay, he had the right concept. But to prove something is a little bit different. I don't think I have enough time to do it here, but I'll give it a try anyway. So as a mathematical proof, you have to start with, you know, theorems. Okay, so you have to know how to say something. In this case, you know, I will say this. Okay, TAC claims the following. Given a number, let's say we call it A, is greater than, given A is an integer, and A is greater than or equal to 1. Given B is an integer and B is greater than or equal to 1. Given P is defined as A times B, then I can make this claim. I can claim that A is less than or A times A is less than or equal to P, or B times B is less than or equal to P. That's my claim. It's a mathematical kind of thing. Okay? It really is saying the same thing that I was saying earlier. The question is, how do we prove it? We don't have enough concepts and tools in this class to really prove it, but it is important that we can do it before we integrate this logic to optimize our program. Because if I don't prove it first and I integrate this logic into the program, potentially I can misidentify a composite number as a prime number. Right? Because I'll be stopping early and say, oh, by the time I get to the square root, there are no factors and this number has to be prime. But if this is wrong, I can mistakenly identify a composite number as a prime number. And that can lead to all sorts of problems. Okay? Why do you think prime numbers are so important? Yeah, it's just some mathematical concept that people use. And why do you think prime numbers are important, especially these days?
Passwords, codes, stuff like that.
Encryption, okay? Encryption schemes, especially with RSA and all the other encryption schemes, they're all based on big, huge prime numbers, okay? In other words, if you can factor numbers really, really fast, you can crack encryption really, really fast too, okay? And that's why prime numbers are important. And that's also why if you use a number that is a composite number, but you think it's a prime number, it makes your encryption key very, very weak. All right? And that's why we don't want to make mistakes like that. We don't want to mistakenly think, oh, this number is a prime number, but in fact it is not a prime number. Okay? So to finish this proof, I won't do it in this class, but it is important. So the next question is, if you are writing software, if you're writing programs, developing programs, it depends on what kind of programs you're developing. What do you think is the importance of mathematics? Okay, let me pose the question even easier. Programmer math classes. How important is it for a programmer, someone who's going to write programs, to take basic math classes?
Pretty
Very
important.
important.
Very important. But I can use a spreadsheet to do most of the calculations. Right?
So how do you know you're using the right forms?
Understand the concept.
Understanding the concepts and understanding the importance of the rigor of proving something is important. I mean, how many of you are on the track of computer science, getting a computer science degree? So you already know what classes you have to take. You have to take calculus.
Yeah.
Do you have to take linear algebra?
Yeah.
Okay? And I can tell you right away, unless you're going to work on any type of actual math programs, you will never encounter matrix calculations again. You will never have to invert matrices ever again. You will never have to integrate or differentiate the equations anymore. The importance of those math classes is to train your mind to think in a mathematical way. Okay? What is the other way around? What if we say, those math classes really have nothing to do with programming, and we'll just let people get their programming or computer science degree without any one of those math classes as a prerequisite?
You have a lot weaker encryptions.
You have programs that are broken to begin with. The moment they roll out of the factory, it's already way broken. All programs are broken. Okay, even Linux, open source programs are probably broken in many, many ways. It's just that they are still under control. Okay, the brokenness is still under control. If people do not have a strong sense of math and they go into programming, it's just going to make it a lot worse. Okay, so that part is kind of important, and I think that will be the last point that I make today. I'll see you guys on Thursday. The program is due on Thursday, so work on it if you haven't done it already.
Check my finding program. I actually uploaded it to the Scratch site.
Oh, you did?
Yeah. Want to see it?
Sure, let me turn off the recorder first. Ready for the next